Hi, this is Mr. Grove, and welcome to my webcast on plate tectonics. My last webcast was on continental drift, and I ended that cast by saying that technological advances in the mid to 20th century has led to a new theory, the theory of plate tectonics. So let's take a closer look. Plate tectonics is something that everybody should have an interest in because we live on the planet, and it explains so much from biogeography, where plants and animals and other organisms are found, but just on the geography of the world and the place that we live. You look at the mountains with awe and you wonder, how long have they been there? They look like they've been there forever. And are they still growing, or are they getting smaller? And plate tectonics explains that so nicely. You look at volcanoes, and who doesn't like volcanoes with roaring lava and pyroclastic flows and entombed bodies at Pompeii? And plate tectonics once again explains that so nicely. And you look at earthquakes and the power that they have to disrupt people's lives and generally just move things around. And again, correlated nicely with plate action. And finally, islands and where they're located out in the middle of the ocean. And look at Japan, you look at the Aleutian Islands, and I'm hoping I get to go to the Galapagos Islands here pretty soon. Again, an understanding of plate tectonics lets you understand so much of the world around us, and that's where we live. And so it's a noble undertaking. So let's take a closer look. Well, just about every student from grade school to college has done this at one time or another. Your teacher is giving you a sheet of paper that shows the earth cut away, and you're like looking at a different layer such as an onion, and you color in the crust and you color in the mantle and you work your way down to the core. So what we have essentially is that we live on the continent, and so we live on continental crust, which rides on a partially molten mantle. And if you take that upper mantle and you take the crust, we call it one unit as the lithosphere, literally the rock layer. And what plate tectonics says is that the lithosphere is broken up into huge plates. And on this graphic, we see these plates right here. And unlike what Carl or Alfred Wegener said about the continents plowing through the oceanic crust, instead we see that the continents are just a part of a whole giant plate that's moving around, riding on the mantle. And none of the plates are defined by the continents themselves. Rather, the continents are just a small part of the plate. And in the case of the huge Pacific plate, there isn't any continent at all unless you count the little sliver of California here on the far east side of the plate. So what we want to do is we want to look at this a little closer up, and one of the first things we'll find is that all plates have boundaries. You know, they have to butt up against one another, as we see the Pacific plate and the Nazca plate, little Juan de Fuca plate. So how do they do this? How do they butt up against each other? And what we find are three boundaries. And the first I'll talk about is what's known as a divergent boundary, where the plates are separating. So you can have places in the world where two massive plates are diverging, moving away from one another. Another type of boundary is a convergent boundary. In a convergent boundary, the two plates are coming together and they're slamming together, and a lot of cool things can happen when that happens. A third boundary is neither one. It's represented here, and in this case the plates are grinding past one another. So there's no convergence, there's no divergence, they are slip-sliding past one another. And probably the most famous area of that is the San Andreas Fault in California, seen in this graphic. From the Gulf of California through Southern California and after north of San Francisco and running into the Pacific Ocean. And it's famous because, of course, all the earthquakes that it has generated over the years. Well, what it turns out is that all of these massive plates, and there's about 7 major plates shown here, and there's well over a dozen intermediate small plates, what they all have in common is they all have boundaries, and they all usually have all 3 of the boundaries. If we just take the Pacific plate, this boundary here, running past the Nazca plate and the Cocos plate, is a divergent boundary. It's actually called the East Pacific Rise. And as we continue up and transition into California, we have a transform plate boundary as they're sliding past each other. And as we move across to the north and to the far west, we have a convergent boundary. So all 3 plates, or all plates, have 3 boundaries. So let's take a closer look at the boundaries. The first one is that we're going to talk about is a divergent boundary. And my graphic shows a mid-ocean ridge. So this boundary occurring at the bottom of the ocean. Weakness in the crust, allowing mantle convection to bring up molten magma and produce lava, which is making new ocean surface. This is a spreading center. In fact, these mid-ocean ridges are the largest geographical features on the planet, running some 70,000 kilometers, roughly like a seam on a baseball as they run around. And what they do is they create new ocean floor. And new ocean floor is created like a mirror image. So new ocean floor created here on the right is matched by ocean floor created on the left. And so what this does is actually there's your plate action. It pushes this plate to the left, pushes this plate to the right. And so we've got new ocean floor being continually made. And a little interesting aside is they used to think the ocean floor was the oldest spot of land on the planet. Now we know it's really the youngest, that there's no ocean floor older than 200 million years, as opposed to the continental crust that can be billions of years old. Now, this type of spreading doesn't just occur underwater. There's several places on the planet where it occurs on land, and perhaps the most famous of those is the East African Rift, the Great African Rift Zone, where the same thing is happening. The crust is weaker here. We've got mantle convection coming up, and we've got new land being pushed, pushing this to the west, pushing this to the east, and neat things happen in between here. So we've got lava lakes, we've got acid lakes, we got volcanoes, and we've got earthquakes. Now, the other type is a convergent zone. So in a convergent zone, we've got the 2 massive plates coming up against each other. In the example I'm talking about, one of the plates is a continental plate, which I'll represent like this, and the other is an oceanic plate, and I'm going to represent as my fist. And I'm do so because the oceanic plate is denser, has denser rock, it's heavier, and the continental crust is lighter. And it was kind of counterintuitive, because you think, wow, man, all the buildings, all the people, all the elephants are on top of the continental crust. But the reality is the oceanic crust is denser and heavier. So as the 2 play chicken and slam together, the oceanic crust dives underneath the continental crust and creates massive earthquakes as it slides down, and tremendous friction and heat. And what happens is the overlying lithosphere and mantle begins to melt. And when it melts, it gets super hot. And because it's super hot, it's less dense than the crust around it. And it rises up in these giant balloons, hundreds of kilometers across. And when they break through the surface, lava is released, and we get volcanoes. We get huge volcanic arcs. Think of the Andes on the South American plate, and the Nazca plate, which is an oceanic plate, has slammed up against South America and subducted. This is called subduction. So we get subduction volcanoes. And every student in a physical science or science class, learns that we have stratovolcanoes or composite volcanoes. And these are generally these subduction volcanoes, the most dangerous kind, arguably the most dangerous kind. We up in Northern California, and I'm broadcasting to you from Santa Rosa, we are in a transform fault area, but we do have a subduction zone. We do have a convergent zone a couple hundred kilometers to our north, and that's the small Juan de Fuca plate that's caught between the mighty Pacific plate and the North American plate, and it's subducting. So you got the Juan de Fuca is subducting down. It's a convergent zone, and it's going underneath the North American plate, and it's melting, and this magma is rising, and it creates the famous Cascade chain of volcanoes that run from Northern California to Canada, with some names like Mount Rainier and Mount Hood and Mount Shasta and Mount Lassen, and the famous Mount St. Helens, who blew up in 1980. What happens when you got two massive oceanic crusts coming together? Now they're both heavy. So they're playing chicken, and one is still going to dive under. Something's got to give, and it's going to dive down just like it did in any other subduction zone, and we get melting of the upper lying crust and mantle. But in this case, there's no continent above it, so we get a volcano breaking out on the bottom of the ocean. We get a seamount, and as that volcano rises and breaks the ocean's plane surface, we get an island arc. And so the famous island arc of Japan comes to mind. And Japan to this day suffers from, I say suffers, the beauty of Japan is created by this subduction, but they have to deal with the resulting earthquakes and volcanic action that also comes from this type of plate boundary. Now, what happens when you get two continental plates coming together? They're both light, and they're playing chicken. They're two cars colliding, their bumpers hitting, and what's going to happen is the hood area of the car in the middle is going to fold. It's going to fold upward. So you've got a continental plate sliding into another continental plate and folding the crust in the middle, and we get great mountain ranges. What comes to mind is India, which is a continental plate slamming into the Eurasian continental plate and buckling up what used to be an ocean floor into the highest mountain range in the world. And you do get a little bit of little subduction, a little under thrust, where one plate slightly goes up, and that even just elevates the plateau, the Tibetan plateau, even higher, and makes those mountain ranges much higher. Finally, you get the transform boundary, and again, it's famous in California. And this, of course, is a cool picture of the San Andreas Fault with the Pacific plate here on the left and the North American plate on the right. And I guess if you had big enough legs, you could straddle two gigantic plates. And in this map, you can see how it really dominates the geography of California. And I personally haven't been able to get away from it. I was born and raised in the San Bernardino area, spent most of my time down here, moved up to the Santa Cruz area just in time to get hit with the Loma Prieta earthquake in 1989, moved back down to Palmdale, down here just in time to get hit with the Northridge quake in 1994. So I've seen my fair share of earthquakes created by this type of plate boundary. Well, there you go. What I haven't talked about is what drives these and what are the evidence for it, like paleomagnetism. But that can be for another webcast. So what I want to leave you with is the Earth's divided into major plates, and all of the features that we've come accustomed to in the world are created by the interaction of the plate boundaries. And the three interactions are convergent, divergent, and transform. Thank you very much.